In this video, we will learn two new Alteryx tools, and they're not really related to each other. So the first tool is the text to columns tool. It's located in the parse category. I've already added it as a favorite, so it's in the same category as the date time tool. And then the second tool we're going to learn is the linear regression tool, which is located in the predictive category, but only if you download it. It's by default not located in the predictive category. So I will show you how to download that in a second. So text to columns is a common tool. I should have covered it in a previous video. A common tool you would use. I'd forgotten to cover it, and I'm almost done with my videos on the tools. So I decided to throw it in this video. It's not related to the linear regression tool. They're not related. I try to do videos on sets of tools that are related, but definitely want to cover this tool. So text to columns, let's bring in some data, or we can create our own data set. I decided to just create my own using a text input tool, or we could bring in some data to illustrate this. But suppose here's our data set. I've already created the data set. I used the text input tool and I just typed. We have two columns, name. I created some random people. First name, middle initial, period, last name, space between first name and middle initial, and between period and last name. And birth date in the format day / month / year. So their birth date. And suppose what we want is we want three columns. We want a column for the first name, Matthew, Jennifer, Rodney, Caroline, Kara. A column for the last name, Friedman, Hogan, Steele, Trice, Stanley. We don't care about middle initial. And then finally a column for their birth year, 1985, 1956, and so forth. We don't care about the day of the month. So to do that, we are going to need to use, in this case, two text to column tools. The first text to column tool, we're going to take this data set and break name into three columns. And then we can only keep the first and the last column there. And then we're going to, the second text to columns tool, we're going to take birth date and break it into three columns. One for day, one for month, one for year, and then we just keep the year. So that's where we're going. So we bring a text to columns tool to the workflow here. Here's the tool configuration for text to columns. Which column do we want to split? Well, we actually want to split both name and birth date, but we got to do it one at a time. You can't do it both in one text to columns tool. You can only do one column at a time. So we want to split the name category. And what's our delimiter? What's going to tell Alteryx to move to the next column? So we want to take the name column and we want to split it into three columns. And what's going to tell Alteryx to create a new column? It looks like the delimiter needs to be a space. The space then will separate first name from middle initial in the period, and we'll also separate the middle initial period and the last name, which is exactly what we want. So the default delimiter is a comma, but we want to replace the comma with just a space. So I just hit space on just one space on the keyboard. Three columns is fine. There are some other options here, but typically with this tool, text to columns, you just use these default options and you just change the delimiter to match to be context specific to your data. So our output then will be our original data set right here, but then we have these three new columns because we've taken the first column and split it into three columns. One column for first name, one column for middle initial period, and one column for last name. All right, now let's use another text to columns tool and take this column and put the birth date column into three columns. Split the birth date column. So we want to do the birth date column. This time our delimiter is going to be a / because that's what we have between month and day, and between day and year. And our output, we have our original data set, we have our first column split into three columns, and then we have our second column split into three columns. And so if we want to just keep, you know, this first name, last name, and then birth year, you know how to do that. You just use the select tool. We don't want name. We don't want birth date. We do want this one. We don't want middle initial. We don't want the birth month, the birth day. We do want the birth year. We need to rename though. We want to rename this column to first name. Rename this column last name. And rename this column birth year. So only 3 columns will be kept as the output, and there they are. So that's the text to columns tool. Next, let's learn the linear regression tool. Now by default, you go to the predictive category. By default, I believe only like these first 3 or 4 tools are here, and you don't see anything else. You have to download these other tools. To do that, go online to Alteryx, log in, it takes a while to log into this website. I don't know why. The website's a little slow. Once you get in here, over here in Product Downloads, click on Alteryx Designer, and then click on the version that you installed here, 20.2, and it takes you to this page. Alright, this is critical. If you originally installed the admin version of Alteryx Designer onto your computer, then all you have to do is install the Alteryx Predictive Tools admin version from this link. And once you install that and you restart Alteryx, when you go to the predictive category, you'll see all these other tools like you see here on my screen, including linear regression, which I've already added to my favorites. Alright, what if originally when you installed Alteryx on your computer, you installed the non-admin Alteryx Designer version? Then what you're going to have to do is you're going to uninstall the non-admin Alteryx Designer version, reinstall the admin version of Alteryx Designer, and then install the Alteryx Predictive Tools admin version. That's what I had to do because I originally had originally installed the non-admin Alteryx Designer version. Actually, I installed the non-admin version, and when I found out that it didn't contain linear regression in the predictive category, or some of the other tools that didn't contain them, I tried to just cheat and install the admin version of Alteryx Predictive Tools, but I had the non-admin version of Alteryx. And when I did that and I restarted Alteryx, I went to predictive category, I saw all the tools like this, but when I tried to use linear regression tool or any of these other ones, it wouldn't work. So I had to uninstall the non-admin version, uninstall this, the admin version of predictive tools, then reinstall the admin version of Alteryx Designer, and then reinstall the admin version of Alteryx Predictive Tools before the thing would work. So don't try to cheat. If you have the non-admin version of Alteryx Designer on your machine, just uninstall that and then reinstall, and then install the admin version and then the admin version of the Predictive Tools. Alright, linear regression, let's see. Let's go to a previous iteration of our workflow. This is our complete workflow that we've been working with through all the videos that I've put up. And we've done a lot with this iteration of our original employee salary database data set. There's a lot connected to this node. Let's go ahead and let's run our workflow here. Make sure that we've run it and then click our output. This should look familiar. We have our employee salary data set. And what I want to do is I want to run a regression. The dependent variable I want to be the salary, the current salary of our employees. And I want to try to predict current salary. I think current salary should be related to their education in years. Should be a positive relationship. Also, I think it should be related to their current time on their job, how long they've been in their job. I would think the more time you've been in your job, the higher your salary is, although that might not be true. So that'd be a positive relationship hypothesized there. Also, I think your salary is probably related to your gender, or I'm going to see if it is. A lot of studies have shown that there's gender discrimination when it comes to salary. So I want to see if males make more than females, holding some of these other things constant, of course. You got to hold things constant. Otherwise, it's not a fair comparison. If the males work twice as much as the females in terms of hours, then of course they're going to make more money, and they should. But they shouldn't make more money if they're working the exact same amount, they have the same level of prior experience, and so forth. And then finally, the fourth independent variable, or the fourth predictor of salary, I think may impact salary. Based on previous research, minorities tend to make less. There's documented evidence of salary discrimination, although it's getting better and better as time goes by. But this variable is coded 0 if they're not a minority, and 1 if they are. So as you move from 0 to 1, as this variable increases out, my hypothesis is that the salary goes down, holding these other variables that we've stated constant. So there's 4 independent variables: education, time on job, gender, and minority. Now the thing with the linear regression tool, both your dependent and your independent variables have to all be numeric data types. Otherwise you can't do it. And all your variables have to have values in each row. There can't be nulls. Otherwise it'll spit out an error. So as far as I know, all these variables, the dependent variable right here, and the 4 independent variables, so there's 5 variables. As far as I know, they all have, there are no null values in any of these columns. We've taken care of that in previous iterations of our data set when we were doing in the previous videos. And you can just hover over the variable. If it says OK 100%, that means there's no null values there. Gender and minority, time on job and minority. But 2 of these 5 variables are not numeric. Education is numeric, time's numeric, minority is numeric, but salary, this is a string data type because of the $sign and the comma, and gender obviously is a string. So what I want to do is I first want to convert salary and gender to a numeric data type. Then we can use the linear regression tool. So to convert salary and gender, we're going to do what we've done before. We're going to use our formula tool. We're just going to put it over here. We're going to take establish a connection here. And what we want to do is we want to convert gender. So our new column, we'll just call it gender 2. And we want that to be if our gender column equals male, then we want a new column. We'll just say 1, else. The only thing else is if it's female, then we want the new column to be 0 and if. And change this to double. So now it's numeric. Our new gender column is numeric. It has a 1 if it's a male, 0 if it's a female, instead of M and F. And then we also want to change our salary column. So let's call our new column salary in dollars. Whoops. In dollars. And we've done this before at least twice in previous videos. We want to replace the character in our salary variable. Which characters do we want to replace? We want to replace the $sign and a comma. What do we want to replace $sign and comma with? Nothing. So that changes $57,000 to 57,000. But that's still a string, so now we need to convert that to a number by using the toNumber function. And then choose double as our data type. Hit run. And look at the output. Now all 5 of our variables, our dependent variable, salary, is numeric. And then our 4 independent variables, education, it was already numeric. Time on job, which was already numeric. Minority, which was already numeric. And gender, which was string, but we've converted it to numeric. So now all 5 variables are numeric. Now we can use a linear regression tool. and we go to the predictive category. It's actually, I've already saved it as a favorite. We drag and drop it and attach it to our output here. Here's our linear regression tool configuration. We can change our model name. We can just say predictors of salary, maybe, something like that. Our target variable is our salary in dollars here, the one that we converted to numeric, not the other one. It doesn't even have the other one as an option because it's not numeric. Our predictor variables are the education, previous experience, whether they're a minority or not, and whether they're male or female, gender. We hit apply. And you cannot see the output from the linear regression tool unless you connect a browse tool. So we're going to connect a browse tool before we run this. Connect it to the R portion. Don't worry about the O or the I portion. You don't use those. Well, they can be used, but you're not going to need them. Not need to know how to use those. Now we're going to hit run, and linear regression takes a while. Depending on the size of your data set, it usually takes a little while. As you can see, it wasn't instant. You go to our browse tool, and here's what the output from our regression looks like from running the linear regression tool. And here we go. Our model is salary. We think depends on these 4 variables: education in years, previous experience. Oh, not previous experience. I went too fast. I'm sorry. Time on job is what I had said, not previous experience. Not this, but this. And we could also put in previous experience. But I feel like time on job and previous experience might be really correlated with each other. We don't want to have both of them in there. Let's just put in time on job. Go back to the browse. All right. We're predicting salary with education in years, time on job in years, whether they're a minority or not, and their gender. Here are the coefficients. So here's information about the residuals. It gives minimum, the cutoff for the first 25% quartile, the median, which is the cutoff for the 50%, 50th percentile, the cutoff for the 75th percentile, or the third quartile, if you want to say that way, and then the maximum. Just some descriptive statistics about the residuals. And here's what you're probably used to seeing when you run a regression, the coefficients. Here's an estimate of the intercept. Here's its standard error. Here's its t-statistic, and here's its p-value. Here's the coefficient on our education in years variable. So the interpretation is for a 1 unit increase in education in years, which means a 1 year increase in education. Every year of education you get, your salary increases by $3,200 with this sample. And that number is statistically significant, statistically greater than 0, because the p-value on that number is very, very small. P-value is 0. And then 15 zeros, and then 22. And the p-value is a probability, obviously, that what you found in this sample, this coefficient being positive, pretty largely positive, the probability that you found that result by pure luck, just happened to take a random lucky sample and get this result. So the probability we did this by luck is really tiny, so therefore it's probably not lucky what we found, and there really is a relationship between education in years and salary. You get more education, your salary goes up. Relationship between time on job in years and salary. Here's the coefficient. Every 1 year increase in your current job, you make $834 more per year in salary. However, this number, although visually it's greater than 0, it's not statistically greater than 0 because the p-value is relatively high. The probability we found this result just by random luck, we happen to take a random sample and get lucky and find this number that's greater than 0, is 22%, relatively high. And so we would probably conclude then that this really isn't statistically greater than 0, and there's not really much of a relationship, at least in this sample, between in this sample or in the population in general, because we chose a random sample, and the size of the random sample was pretty nice, pretty large, much greater than 30, we would conclude that there's probably not much of a relationship between. You can't increase your salary by working more years. So it's like a glass ceiling for these people, which is unfortunate. And then the two variables that are probably of most interest, there seems to be a negative relationship between whether you're a minority or not and your salary. Moving from 0 to 1 on the minority variable, so a 1 unit increase in the minority variable means moving from not a minority to being a minority, leads to, on average, a decrease in salary of $5,200, and it's highly significant. That is, of course, holding these other three variables constant. Take two people, one's a minority, one's not. They both have the exact same level of education. They both have been at their same job for the same amount of time, and they're both either a male or a female. They're both the same gender. The minority will make $5,000 less than the non-minority. That's what the interpretation is, at least with this data. And so that could be evidence of salary discrimination by race, but there might be some other variable we're not holding constant here that may explain this other than racial discrimination salary-wise. Like, for example, maybe for some reason the minorities work less hours than the non-minorities. Number of hours worked isn't in the regression, but if they work less hours, they should get paid less, and that's not unfair. If they work the same hours and everything's the same as the non-minority, then they definitely should not get paid less. They should get paid exactly the same. Gender, if you move from 0 to 1 on this variable, so a 1 unit increase in gender leads to a $9,031 increase in salary per year. And remember, we coded gender. 0 is a female, 1's a male. So males make $9,000 more than females, holding constant their whether they're a minority or not, holding constant their time on job, and holding constant their education. So this could be evidence of gender discrimination in salary, unless there's something in there that we're not holding constant. Maybe the females work less than the males, a lot less, and that's why the males get paid more. And that's not in the regression, how many hours they work per week or per year. Salary definitely should depend on that, and that could be the reason here. But if they're working the same number of hours, again, we shouldn't observe the difference unless there's a case of gender discrimination. So this is the linear regression tool. And also it spits out the adjusted R-squared, which for this one is 50%. So we are able to explain 50% of the variation in salary by these four variables, which means there's 50% of the variation in salary that's not explained by these four variables. There must be some other variables that explain the other 50%. We have the S statistic, we have its p-value, we have an analysis of variance down here, ANOVA. That's what the linear regression tool does. And you can look at one more thing as well with the linear regression tool. You can look at plots of the residuals, which are cool. This plot is probably the one you want to look at. The residuals plotted against the fitted values. You're kind of looking for the red line to have a slope that's not statistically different than 0. Otherwise, your model might be a poor fit. So anyway, that's how you use the linear regression tool. And we went through the text to columns tool as well earlier. That concludes this video.